Here at the Alan Turing Institute, our mission is to make great leaps in data science and artificial intelligence research in order to change the world for the better.
This podcast explores the research, ideas and technologies behind the data revolution with the people responsible for shaping our future.
Welcome to the Turing Podcast. Hello everyone and welcome to another episode of the Turing Podcast. Just to note that the audio quality for today's episode is a little bit lower than usual. It's the very first episode that we've managed to record back in the office at the Alan Turing Institute, and we're still working on our new setup in the brand new media suite that we have. So bear with us, future audio quality will hopefully be even better than what you're used to. A lot of the episodes, as you might imagine, that we've released over the last 2 years have been recorded at home over Zoom with our podcast guests, and so we're looking forward to having the opportunity to get people back in the office in our new studio and record them properly. This episode we did do that, but not with the best possible audio equipment, so bear with us and enjoy. Hello everyone, welcome to the Turing Podcast. I'm your co-host Ed Chalstrey, and today I'm joined by a new co-host, Christina Last. Christina, hi, welcome to the podcast.
Hi.
So Christina, you're new to the Alan Turing Institute. What's your role here and how did you come to be at the Institute?
So I'm new. I joined this summer at the Turing Institute. I'm a member of the research engineering group alongside Ed, and my background is quite hybrid. I kind of came to AI sideways from a geography degree, but I'm really interested in the use of AI, and we'll get onto that later. But within the idea of looking at how do we understand urban inequality and use these kind of processes to understand geospatial concentration and looking at kind of open source geospatial data around that as well.
Nice.
So I'm really excited to be on the podcast team and have super interesting conversations.
Yeah, so Christina's part of the same group at the Alan Turing Institute as I am, the research engineering group, as she mentioned, and I've roped her into doing the podcast as well. So thanks for that. No, I'm just kidding. You volunteered, I think.
Yeah, I remember kind of hearing about it during my application process and listening to a few. Yeah. It's good interview prep.
Exactly, yeah. So today we're joined by another member of the research engineering group at the Alan Turing Institute. We're joined by Dr James Geddes, who is a Principal Research Data Scientist, and we're going to be discussing the problems with artificial intelligence. James, welcome to the podcast.
Thank you very much, Ed. It's great to be here.
So James, before we get into talking about AI and its problems, can you tell us a bit about your background in science and what led you to be your current role at the Alan Turing Institute?
Sure. You've probably heard this phrase before. I don't know, it probably originated from James Hetherington, but again, I have less of a career and more of a careen. So
define careen.
Well, I sort of bounce around. So I'll tell you what I've done. So I have a PhD in theoretical physics. So I've got quite a mathsy background. But then I did a stint as a management consultant, which is quite different. And then I ran my own company doing sort of analytical consultancies to small to medium-sized businesses. And then I worked in government, in the civil service for a while, which indirectly is how I've ended up at the Turing. I can tell you more about that if you like, but I worked in the then Department of Energy and Climate Change on climate change matters. And then I did a stint at a management consultancy, but in analytics, in sort of a data science capacity. And then I came here.
Okay, so you've really gone from doing the physics PhD, you've gone through the world of business and the world of government, and now back at
I've done them all.
back at the Research Institute. So which is the best place to work?
This is the
business
best place
or
to
government?
work.
Okay,
but what's nice about this is that so there are trade-offs in business and government, I think. And maybe just to be slightly simplistic, business, you feel like you're having an immediate impact in business, I think. You have to make decisions and they have an effect. But, in the end, it's about making money. And maybe you're lucky and you work for a company whose sort of mission you really care about. But for most companies, it's about money. In the civil service, I think I was quite surprised when I joined to find, there's this sort of yes minister archetype of the civil service as being almost pure functionaries who are just concerned with the status quo. And I found that to be not true at all. I found like a large group of extremely, people who really cared about making the country work better and doing things well. So you do feel there's this sort of greater mission, that you are in fact a public servant, and that is a good feeling. But the pace of being able to change things is so slow and difficult. It just is hard to turn the ship of state. And of course you're working at the pleasure of the minister. So the decisions on exactly what to do are not yours. Your job is to advise and to implement.
So you're saying government is slow, business is fast, maybe is science somewhere in between?
It can certainly feel that way, I think. I don't know about science, but here I felt that I think we all feel like we're trying to improve the world, genuinely, but we get to sort of make decisions that affect how what we work on and how we do the work we do, and so I think there's a bit of best of both worlds, I think, to be working at, which is why I like it.
And how did you come from the government role to the Turing? You mentioned that.
Oh yes, right. So when I worked in government, there was a project called the 2050 Project, whose goal, the idea was at the time, the UK had committed to these targets for CO2 reduction by 2050, and the question then is, okay, well then how do we do that? And I think traditionally, what the government would have done is it would have commissioned some kind of analysis by an external consultancy, and the question would have been, could you build a large model and optimize, and what is the correct pathway to sort of zero or as it happened, 80% carbon reduction. But at the time that I joined, a professor of physics, David Mackay, had just joined DEC as chief science advisor, and he'd joined partly on the back of a book that he'd written called Sustainable Energy Without the Hot Air, which is available online for free, by the way. And in it, he basically asked the question, could the UK live on purely renewable energy sources? Sustainable energy sources. And the book was a series of chapters, and each chapter did a sort of physics-like back-of-the-envelope calculation, either about what amount of sustainable energy could we produce, or how much do we actually need for transport and heating and so on. And then the book sort of added them all up. It's a lovely book, it really is. And so what we decided to do was to try and turn the book into a model, to sort of make the book come to life and allow the user of the model to play with the the scale of change that they thought was possible in each of the sectors. It's very different. So the normal approach in government is, what's the cost minimization approach?
Yeah.
But the thing here is that, well, that's not the question. The question is, what are we going to do? And we have choices. And the uncertainties over those costs, of the costs of the choices we make, are very large, actually. And so the cost minimizing approach, it's very picky. And anyway, there's so much uncertainty. So the real question is, what's the impact of certain kinds of change? What would be the impact if we didn't build wind farms, if we built lots of wind farms, if we built wind farms on twice the rate we've been doing and sustained that all the way through 2050? I mean, just what's the range of possible alternatives? So we built this model, which we call the calculator, because it sort of just added things up. And I think that was a super successful idea. During that period, David and I had concocted we had two views on why analysis in the real world is sort of difficult. And my view was that what civil servants have available is Excel. And Excel is an amazing tool, but there are a number of well-known problems with trying to build large-scale models in Excel. All the things that we talk about in the research engineering group, reproducibility, version control, modularity, abstraction.
And just for the listeners' benefit, you're literally talking about Microsoft Excel spreadsheets, and that's like the commonly used tool for scientists in government, I guess, or
for civil servants.
For civil servants,
yeah. I mean, there are some groups, have other tools available, but they tend to be quite specific groups, and in my sense, is a lot of the analytics is sort of outsourced anyway. So if you're a general civil servant like I was, you get Microsoft Office.
Yeah.
Which is no bad thing, but spreadsheets don't do everything, and you tend to use that tool because that's what you have, and then you build more and more and more, and then suddenly you've got this enormous, great Excel model that is quite hard to manage. But I mean, well, there are benefits, right? So a number of other countries adopted the model that we built, the 2050 calculator, and adapted it to their own country. Which was fantastic.
And that was based in Excel.
Yeah. So every time we would start, and we got to go to China and help quasi-governmental agency in China build the version 2050 calculator. And every time we did this, I sort of said to the team, look, it's such a pain to try to update this model.
Yeah, right.
Can't we just write it in some sensible programming language? And the team said, I think quite rightly, yes, it is a pain, but the only reason we've got so much traction, the reason that other countries have sort of looked at what we've done and said, oh, we should do that, is because it's in this Excel, which everyone knows how to use.
Everyone's familiar with the traditional spreadsheet.
Exactly.
I've heard horror stories about like the results of scientific papers turning out to be very different because when someone's drags down the selection on a spreadsheet to give a slightly different formula, it's resulted in different results for some and that's stuff that's been really impactful to policy in the world.
Yeah, well, I mean, the canonical example I think is the Reinhard Rogoff paper on.
That's probably what I'm thinking of.
Yeah,
so it's an economics.
It's an economics paper on, and I'm not an economist, so it's not clear to me that the error affected the conclusion, and it's not clear exactly to me how much policy was really determined by the paper, but it sure looks like policy was determined by the paper. A lot of people cited this as to why we should have austerity.
Right.
But there's other examples. There's the loss of the a lot of the COVID tests recently. The count was lost because someone passed data using Excel and it chopped off it.
I remember that news story last year.
Okay, so I mean, there are reasons to use Excel, and there are also reasons not to use it. So I had some ideas for how we could fix this problem, and at the same time, David, his big thing was that it's hard for people to work with models that include uncertainty, and the world is just uncertain, right? I mean, there are things we want to know about the world, but we can't know them directly. So we make observations of things that we can observe, and that implies, that gives us some knowledge of the thing we really want to know, but not perfect. There remains some uncertainty. If you enact a government policy and you want to predict what's going to happen when you've made this policy, well, there's a lot of parameters you have to assume about how people behave and the costs of things, but you don't know them. So one problem is, how do you build models that allow you to predict, for example, the impact of policy interventions, but show how uncertain you are? And then, importantly, you spend a year and you observe what's happened, and it's not exactly what you predicted, or it's within the bounds of uncertainty. But then how do you take the observation about what has happened, feed it back through the model, and get better estimates of the things that you need to know that you don't know? So both of these things are quite hard to do in Excel, and therefore hard for the civil service to do. And especially the second one, especially the updating your knowledge based on observations. So, David is the reason I'm a Bayesian, basically, and everyone should read his book on.
Can you explain what you mean by
that? Yes. Let me finish this story,
then
you can ask me about Bayes. Yeah. So anyway, we had an idea that we could sort of work on these two problems. So. And the Turing seemed like an excellent place to go work. And so David was appointed as a fellow, and I was appointed as the first member of the research engineering group. And then, as you probably know, he tragically died before he could take up his position here. So, so that was a bit crap. But anyway, that's why I'm here.
But when you joined the research engineering group, you did get the chance to look at this very problem. So can you tell us a bit quickly about the project before we talk about AI? Tell us a bit about the Excel project.
The project is called NoCell, and you can't don't go and try and download it because we've had so I've had some time to work on it, and it's now a bit more concrete than it was when we first came here. Effectively. So a lot of people have made this observation that if only you could combine the best bits of Excel and programming languages, maybe that would be great. In my view, typically what they tried is to start with Excel and add programmatic capabilities to it.
Yeah.
Right.
And what I would like to do is go the other way. So I would like to write a little programming language, ideally of the sort that it's convenient to build models of the kind that governments like to build, which produces as output an Excel model that does the same thing. So the idea is you write a program, but the compilation target, if you like, is Excel.
Would you be able to import it into Excel?
That is the first question that everyone asks. You mean if you change the model, does it go back into the program?
Well, it depends how you think people would use it. But I would say that usually when you develop a model, you want it to be interpretable by another team who may not know about the programming language.
Yeah. So the idea is you'd write your model in this language, and then you say compile, and you get an Excel spreadsheet, and that's the model. So then you could give that to someone else.
Yeah.
And all they need to understand is how spreadsheets work.
Exactly. I mean, I would like this. I've built a lot of spreadsheets in my time, and I still use spreadsheets even here for sort of a lot of operational stuff because they're just really convenient. But I really would like to be able to generate a spreadsheet from programmatic source. Like I'd like to be able to write a little program and have it, because it would solve a lot of the problems that programming languages try to solve: abstraction, modularity, version control, reproducibility. So, so I think we've got a bunch of ideas and a bunch of code does some stuff, but it's not finished by any chance.
Yeah, and it sounds like a fantastic idea anyway, because you're doing is hopefully marrying the world of data science and possibly AI with the world of civil servants using spreadsheets which end up determining government policy and all the rest of it.
Yeah.
And it does seem like those are two worlds that are probably worth marrying.
Yeah.
But James, so we got you on the podcast to talk about AI.
Right.
So let me ask you first. Are you?
You've misquoted the title of my talk.
What was the title of your talk?
The Problems of AI.
The Problems of AI. What did I say?
The Problems with AI.
Problems with AI. I do apologise.
It's all right. The problem is the title of my talk is a pun.
Okay.
So.
Is it? I don't get it.
Yeah. So this was a lunch and learn I gave. His
talk that James gave a talk internally at the Institute to which I attended.
So the
subsequently misquoted.
The pun, it's okay. I think the announcement went out as the problems with AI. Yeah, so I wasn't really talking. I didn't really want to sort of say AI has problems and this is why it doesn't work.
Right.
What I wanted to say was. So what I mean. So the question is, what is AI? Okay. So, and what I felt before is that there are lots of explanations of AI. Some of them are very high level. They're sort of, look, it does this really cool thing, isn't that amazing? And then some of them are overly technical, and you're sort of lost after the first slide.
Yeah.
And I was trying to find a way to say, to give an explanation that was right but not technical, and could help you to answer the question. For example, suppose you have a problem and you think AI can help. Well, there are some problems that AI, as we know it today, can help with. And there are some problems where we don't know how to solve that problem today. So the question is, how could you tell? So what I was trying to describe was, what are the characteristics of the kinds of problems that we can actually solve today with the kinds of AI that we know how to make? Mm-hmm. Because there's only a few, and it's certainly not all of them. So if you understand what kinds of problems can we solve, then you understand what kinds of AI we actually have. So that was the idea.
That makes a lot more sense.
Yes,
I
do. So the problems of AI.
Exactly.
Before we go delving into that, James, can I ask you, are you an AI researcher?
No. I mean, again, what am I? I don't know. I guess I'm a data scientist, so I think that makes me AI adjacent. So, I've got, my name is on papers, which I guess are in the field of AI, but it's not my day-to-day job advancing the field of AI.
But we're certainly working in an area where we see a lot of things which are called AI.
Right.
And then at some point you've got to describe, well, what do you mean by artificial intelligence? Is this quite a generic term, like, for instance, computing, which could refer to a lot of different kinds of things?
Right.
But you did at least have an attempt at categorizing the different kinds of things that we might be referring to when people, be they, ordinary members of the public or the media or scientists, what do they mean when they say AI? You gave us a few different categories. I'll just list them and then maybe we can chat about what each of them mean. So one of them was simulation. Another one was good old-fashioned AI, otherwise known as symbolic AI. And then the most, perhaps to some of our listeners at least, especially if they are themselves scientists or practitioners, the most commonly, the one they will have heard of the most is machine learning.
Right.
So could you talk us through these categories and what was your thinking process between splitting these types of AI into these categories?
Yeah, sure. So just stepping back a second, the definition I gave of AI, which was a bit trite, was it's anything done by a computer that looks intelligent. And it's very. I think it's quite good because, it's sort of an operational definition, but it's also a bit subjective. Like, well, okay, is that intelligent? And in fact, I think what we think of as constituting intelligence has changed. Basically, as soon as AI can do it, we don't think it's intelligent anymore.
There's also, and we shouldn't go down this rabbit hole right now,
Sure.
but there's also the question of like, what is intelligence? In the first place?
No, absolutely.
Yeah.
So I think we don't have a good answer to that question. Right. So then, so then I'm going to use this very, this easing out, which is to say, well, if it quacks like it's intelligent, then it is intelligent, right? So
yeah, right.
Which I think is sort of fair enough for most people, right? But the point is that we don't have what is now being called artificial general intelligence. Like, we don't have all of the fictional robots you see in the movies. In fact, so in my talk I talked, there was C-3PO and Wall-E and
Terminator.
The Terminator's probably there, the robot from Ex Machina.
Yeah.
I didn't have Aurak from Blake 7, which our colleague called me on the other day. But anyway, none of those things exist.
I don't know what that is.
Yeah,
as I said,
far
around
too young.
lunch table.
It is amusing. I think this. So I've lived through now 3 AI ages. There's been 3 sort of booms in AI. This being the third. The first one being about the time I was born, and the second one sort of around the 80s.
I won't ask you when that was.
I was born in 71, so AI sort of started, say, maybe in the late 60s. So there's been a boom and a bust, and a boom and a bust, and here we are in the third boom.
Just thinking about, like, as a term, like, when was it coined? Would people like Turing have said AI, or would have been later than that? I don't know.
Well, he did talk about, famously the question of can a machine think, and so he proposed the imitation game. But I don't know, but I rather suspect the term was coined in the sort of late 60s. There was a famous, I'm going to get the details wrong, but the people of that era, was it McCarthy? I don't know. Anyway, there was like a summer session, probably at MIT or something similar, and with the people whose names then became recognisable as AI researchers, and I think they coined the term artificial intelligence. Although they also thought they'd have vision done by the summer. This was in '68 or something, which clearly turned out to be.
Well, is the difference between those conceptions of AI about the problems that they're addressing, or is it about the kind of technology or the types of those AIs that they were?
Yeah, both of those things. I don't think this is again. I don't know, but I don't think at the time we thought of it as changing the kind of problem. But as I look back and see it, I think it does change the kind of problems that we worked on. So here's an example. So, one thing that often appears intelligent is an ability to make a prediction. So, here we are today. I'd like to know what things will be like tomorrow. And I think it's reasonable that if you can tell me something about tomorrow and that turns out to be true, there's something clever there, right? One way of figuring out what's going to happen tomorrow is to simulate the world. So if you happen to know everything about the world, or at least the bit that matters, and exactly the laws governing the evolution of the world, well, then you can run those laws on a computer and you can make a prediction about tomorrow. So, the weather forecast is precisely this. So you take measurements of all the atmospheric conditions around the world, you put them in a large computer. We know the equations of fluid dynamics and heat transport and so on that govern atmosphere. I mean, there's a lot of uncertainty here, right? So you can't simulate down to centimeter level, and you can't take measurements everywhere. But you check it in the computer, and you crank through deterministic physical laws, and you make a prediction. And that says, okay, it's going to rain tomorrow. I should take an umbrella. That's quite clever. And so yeah, I think that's a kind of AI, and and I think actually, when people talk about AI, the term is so broad in common use that I think it covers this just fine. If the computer was making predictions of something, you'd be like, "Oh, that's quite clever. That's probably AI." So yeah, I think simulation is a kind of AI, although it's not the kind we normally think of. But at the Turing, there are a lot of projects that involve sort of physical simulations of real objects. So there's the Bridge project, famously, and there's the London Air Quality project, and so on. Now, of course,
we have Turing podcast episodes on both of those.
Yeah,
so
exactly.
Take a little look back through the back catalogue.
Yeah, and they're not just simulation. I mean, just to give them their due, these projects are quite clever because they do, in fact, try to understand uncertainty, which is a deeply difficult subject. But so they're more than just pure simulations. But they are simulations, and now it goes by them. There's this idea of a digital twin, which is this thing people talk about, where the idea is you build a simulation of some part of the world in the computer, and then you feed it measurements from the real world, and it updates itself to kind of stay in sync. And then if you want to say what's going to happen, you can run it a bit faster than the real world and see what's going to happen.
Yeah.
So I think simulation is definitely a kind of AI broadly construed.
So that's simulation.
Yeah.
And I guess another way of thinking about that is it's some kind of program or computer model that is making a prediction about the future.
Yeah.
Given the input data that you have. But I suppose in this example, because you're talking about a separate category to one of the others you mentioned, which is machine learning, we're talking about a system which, as you said, like you're programming in physical laws, for example, if it's a model of the weather or a bridge or some other kind of physical system that is a representation of it's a simulation of a physical system. And so, of course, the way you're going to try and program that is that you're going to have deterministic rules, as you said, which are based on the physics as we understand them in the real world, and then that should just work. Although I guess and this is just a matter of opinion, but that kind of thing to me, if anything, seems like it's definitely not AI. It's definitely not but just because it's not, it's like an equation, but more complicated.
Yeah, but I bet you can't think of a definition of AI that includes the things you want to include, but excludes this without being out.
That's probably fair. Yeah.
But I think you've hit on a good point, right? So you look at it and you say, well, it's clever, but the cleverness is sort of in the actual discovering of the physical laws. I mean, if it's gravity or something, it took Isaac Newton, who's a bona fide genius, right? So and he needed a whole slew of historical geniuses who made measurements and so forth before. So that's clever, but that's done already by the time you come to do the computer thing. And then, of course, you have to write the software that solves the equation, and numerical software is notoriously, it's tricky, right? You've got to make approximations. You've got to be sure those approximations don't invalidate your calculations. You've got to do them quickly. It's no good doing the calculations slowly, so that by the time they're done, the thing has already happened. It's quite clever to design a program that can do those calculations, but somehow that also, and you have to know the initial conditions. You have to have measured where everything is right now. I mean, you have to know quite a lot about the problem before the computer even gets a look at it.
Well, that's why I feel like it's like the intelligence is taking part inside the human, whereas the computer is just running the instructions.
But of course, the computers are always just running the instructions, no matter what kind of AI we're talking about.
Is that true in machine learning?
Yes.
Okay.
I'm going to upset a lot of people. I'm going to upset so many people. I mean, I think we can talk about machine learning, unless you want to go via
Well, I think
Yeah.
I struggle with this point about it being deterministic and almost, predefined set of rules, and the engineering being the smart bit. Like, for me, it's always been the AI has had, and the machine, like, obviously my concept of AI is much more refined around the machine learning point.
Right.
And that's because it's kind of creating these relationships that we aren't explicitly defining, which is how I see that in contrast with something deterministic like a simulation.
And
so
I think
if you could explain that,
yeah,
that would be useful.
Sure.
I think the way in which he hopefully can explain that, and I think is the example that he gave in his talk, which you talked about the simulation category, but the other category that isn't machine learning was symbolic AI.
Yeah.
I'm curious about that sort of.
Yeah, and what should help us to differentiate that from machine learning is that in some cases they've been applied to the same sorts of problem. So, for example, the problem of designing a computer program that can beat a human being at chess was something that was solved before machine learning was even thought of being used to apply to that problem by symbolic AI. So, yeah, maybe you could talk a bit about that and make that differentiation there.
Sure. We're getting even more sort of tendentious, I think. On this one. So look, good old-fashioned AI. So, originally we thought, well, that intelligence is about cognition, about thinking, about reason, and reason's about logic, for example. And so what we should try to do is to figure out the laws of thought, the rules of logic, and then we'll just have the machine do that somehow. Okay. So how does that work? Well, so a good example is chess, I think. So before we solved chess with computers, everyone thought that if you could have a computer that would beat you at chess, well, I mean, the old joke, right? There's a dog in a pub playing chess, and the man said, "That's incredible. Your dog plays chess." The man said, "He's not that good. I beat him 2 times out of 3." Right, but the joke is that, of course, it actually is quite clever to play chess. Dogs don't play chess, right?
Yeah.
Okay, so we attack this problem, and the thing is, it turned out that we. So how do you get a computer to play chess? So what we didn't do is we didn't think, well, I mean, we obviously did think about how people play chess, but it turns out the way we solved the problem with computers was not how people do it. I don't even know that we know how people solve these problems. But the computer approach was actually conceptually extremely simple, right? So the problem with chess is, like the simulation, you know everything about the part of the world that matters, right? You can capture in a computer easily, if you're a programmer, the positions of all the pieces on the board, right? That's not a problem.
So in this case, instead of knowing the laws of physics, you know the rules of chess.
Exactly. But unlike simulation, the problem is there's no rule that tells us from here necessarily the next state is here. Like with a rocket going to Mars, there's a rule that says if the rocket is here going this fast, then a second from now it'll be over there going that fast. Okay, but there isn't a rule with chess, and the reason there isn't a rule with chess is you have an opponent, and the opponent has options.
Yeah.
And we don't know how to simulate your opponent.
Right.
Okay. But we do know the rules. That's a lot of information, which means we know not what will happen, but we know everything that could happen.
Yeah.
So your opponent only has a finite number of options open to them, and you can enumerate them all. So in principle, chess is really easy. You represent the starting position in the computer, then you represent every possible legal opening move. There's 20, I don't know how many there are. And then for each one of those, you enumerate every possible legal reply. So I don't know, there's 20 of those. So now we're up to sort of 400 possibilities. And then for every one of those, you enumerate every possible legal reply, and you just keep going. And eventually, so it's like an enormous tree. So you start with a single board, and then you get 20 boards, and then each of those, ramify into 20 boards and so on. It's like a big tree. And at the branches of those trees are the ends of games that are either a win for white, a win for black, or a draw.
And those are all of the possible games
And that's everything
that it's possible to have.
Right. This is all, by the way, in principle. So
Yeah.
you don't do that, but you could, in principle, that's what you do, right?
Yeah.
Then you ask yourself, you just sort of start at the end now, and you work, and you know which of those are wins or losses or draws, and then you work back. So if from any position I know that you, Christina, have a move which is a win for you, I know this position is already lost for me. Right? If I give you the board and there's one move that you could make that would be a checkmate for you, I've already lost. So that I know that's a loss. And now if we go one step back, now it's your move, because and supposing that every move open to me has the characteristic that after that there's a winning move for you, well, then you know that from the previous position that is a win for you, because everything that there's, if you make this move, then everything that's available to me is a loss for me, which means you win. So you just propagate these wins, losses, and draws all the way back to the beginning, and then you choose a move that guarantees a win. Okay.
So people figured that out, and following that principle, created a chess algorithm that could beat humans as early as the 1990s.
Yeah, not quite, because the problem is you can't do that in practice.
Oh, because there's just
too many.
Yeah.
Right.
There'll probably be, I don't know. Yeah, I don't know what the complexity of chess is, or like how big a number that we're talking about.
Well, so there's a rule that says,
but it'll be far more than any.
Yeah. So let's suppose there's 10 moves,
research.
10 positions each move. There's more than that. Let's suppose there's 10. It makes it easy. What's the rule if the game goes more than something, it's a draw? Is it 30 moves or something? Suppose it's 30 moves. I don't know what it is. Okay, so that means there's 10 to the 30.
I apologise to any chess player listening.
Yeah, but the principle is right. There's 10 to the 30 possibilities by the end, which is a lot.
Yeah, exactly. It's a big number.
So we cheat. So first of all, there's not a cheat, but a clever idea is that if I'm in a position and I enumerate all your options, and one of them is checkmate for you, I know right away. I don't even have to explore the other ones all the way down, because you're going to choose that one. So I don't even bother.
Yeah.
So I prune the tree.
Right.
So that's one easy win. But even that's not good enough for chess. Noughts and crosses is probably good enough, but chess is not good enough. So then we think, what are we going to do? So what we do is we say, well,
we the computer algorithm.
We the person writing the computer algorithm.
Okay.
Right? we say
Big distinction.
Yeah, we say, look, okay, we can't follow these all the way to the end. So what we'll do is we'll go out as far as we can in the time we have available. And by the way, by the end, Deep Blue was evaluating something like 10 million board positions per second. I mean, that's insane, right? That's absolutely. Imagine, and it only just one. I mean, imagine what is it that humans are doing that you can, force a draw on a machine that can evaluate 10 million board positions a second.
Yeah.
I don't know what that person is doing, but not doing that. Okay. So you go as far as you can in time available, and you won't be at the end. It's not an end game. So you don't know if this position you've got to is a win or a loss or a draw for you in the end. Uh-huh. So you guess. You invent a rule that tries to assess somehow how good this position is for you. A heuristic. It's a heuristic because it's a guess. It's not guaranteed. So, for example, over the years, chess players they assign values to each piece. A pawn is 1, a knight is 4, and a rook is 3. I don't know what the numbers are, but they're something like this. So you could just add up the numbers, the values of all your pieces, and subtract the values of all your opponent's pieces, and that's a quick and dirty assessment of how good this position. I mean, certainly it takes into account material, right?
Yeah.
And there's other clever things you can do. You could talk to, grandmasters, and they say, well, it's important to control the center square, so maybe you can have half a point there, or blah, 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 blah. Then you use exactly the same rules. You go out as far as you can, then use the heuristic to evaluate the position, and then propagate that back.
Prune the trees.
You prune the trees with the thing we talked about before, And in addition, you assess a position not by a guaranteed win or a loss, but by this heuristic.
So of the
value.
prune trees, you're then deciding which move to make next.
Yeah, because it sort of looks good to you.
Yeah.
Because as far as you can tell, 10 moves ahead, or 5 moves ahead, or whatever, it looks pretty good on material. Okay, so that's what we did. Plus, in Deep Blue's case, we also programmed in an enormous library of potential opening. I mean, the reason I don't play chess is as a kid, I was trying to learn chess. Oh, this is lots of fun, I'll learn chess. And then I went to the library to get a book on chess.
Yeah.
And there was a book in the library called something like The Queen's Gambit Declined. And I figured if you need an entire book to talk about a reply to an opening, I don't want to know anymore, right? But all of that stuff is in the chess computer. Plus, the end game is also basically solved.
Right.
Like, with only a few pieces left, you can pre-compute who's going to win by just playing out all the games.
And is there a way to connect those two ends?
Not through the mid-game,
Right.
no. The mid-game is the tricky one. But, the opening gets you a long way, and then the mid-game you play with this method we've talked about, and then when you get to the end, you know what you're doing.
So in a way, is similar to the simulations, is a symbolic AI chess engine just a summation of human knowledge that an individual human is going to find very difficult to both know and realise in their chess playing ability, whereas a computer program can at least have all of its different writers of its software, and it will remember all of those heuristics and
so they get better
strategies.
through two ways. One is the person invents better heuristics, and the second way is the machine gets faster, and so they can explore deeper down the tree, down the game tree, which is where its main advantage lies.
Yeah, and they can it can explore a bit further down the tree than a human can think a number of moves ahead, perhaps.
Right.
Okay.
That's right.
So that's an interesting distinction then, because it seems to me like you've got a distinction here between both on one hand the symbolic AI chess programs and the simulations, and on the other hand machine learning.
Because you're thinking, but where's the cleverness in the machine? What did you have to know about the problem to even get it going with symbolic AI? Well, you have to know how to represent the world. Lots, right?
Yeah.
How to represent the world, and how to represent, and you had to know the rules that govern the possible ways the world could be, even if you didn't know which one it would be. So that, we actually have computer programs that help mathematicians prove theorems in maths, which is also kind of amazing, right? That's clever. Maths is hard. And what do? Well, the rules of logic are mechanical. The rules of logic say they give you a set of ways of writing down logical statements and a set of rules that say if you've written down these statements, then you may conclude this statement or that one, but not these other ones.
Right.
And so then effectively, it's like chess playing, it's more than this, but effectively you just search all the possibilities. And so in the end, you've constructed a logical proof, and that looks really clever, but what you've done is you've searched through and what's clever about it is there were too many possibilities to really search, and so some human cleverness went in telling the machine, which ways look promising.
I see. So as a human coming up with those mathematical proofs, you're in a certain sense relying on good fortune for coming across it, but also maybe many decades or hundreds of years of getting there and building on the
there were lots of
previous
heuristics.
people.
I think my sense is these theorem proving programs. In fact, in the field of so programming is maths really, just to be even more tendentious. And so writing a computer program is, it turns out, very much like proving a theorem. And so there are software that help you write correct computer programs.
Yeah.
And they work in very much the same way as theorem proving, because it turns out to be effectively the same thing, which is a topic for another day. And they involve tactics. which I understand, I could be wrong here, this is definitely going way out of my field, are basically heuristics for what kind of proof techniques to try next. But in the end, it's yeah. So you have to know a lot before you can even get going on the problem with this AI. But we got a long way. Like we did chess, we did North Crosses early, then we did chess. We had programs that would stack blocks, and they'd answer questions about why certain blocks were stacked in certain ways. There's lots of other parts of good old-fashioned AI that I'm not even talking about, like knowledge representation. But in the end, we couldn't solve the problems that we thought were really easy. Like, here's a number, and I'll write it on the whiteboard. What number is that? Just recognise that number. And it turned out those were really hard. And
you mentioned the people at possibly MIT or somewhere who in the 1960s wanted to work on computer vision.
Yeah, I thought they'd be done by
thought, this will be a simple task.
We thought that'd be easy.
Yeah.
Well, recognising like what are the words that I am saying? Not even what do these words mean, but what are the words that I am saying? That speech recognition turned out to be super hard. Here's a photo of an animal. What animal is it? That turned out to be really hard. And the reason that we got stuck was that there were two reasons. Well, so one reason is, of course, you have to know the rules to do symbolic AI, but what are the rules of what's a number 7?
Yes, yeah.
I don't know. It's like two lines at an angle, except one's horizontal. But of course, in the real world, well, first of all, I don't know what the rules are, so I've got to make that up. But secondly, in the real world, number 7s, if I write down a precise rule about a number 7, real 7s are never like that. You know, it's like the line's a bit tilted, or there's a slash through the middle, or one of the lines broke because the pen came off the paper. But it doesn't matter. You see it's a 7.
Mm-hmm. And then if your AI is trying to determine the difference between a 7 and a 1, it might be a lot more easy for you to understand that than for the machine. But then you can't even write down.
How do you even articulate what the rules are?
Articulate what your own understanding of what is a 1 and what is a 7
precisely
is.
So if you don't know how to say what the rule is, how to recognise the answer, you can't even get started on. I mean, there are other reasons that the Symbolic AI program sort of got stuck. And one is that if you ever talk about real-world examples, the problem is that actually there is so much knowledge about the world, and almost none of it is relevant to any particular problem. Like if I ask, why are you wearing a t-shirt and not a jumper? Well, I mean, the room is white, there's 3 of us in the room, we live in London, it's grey outside, it's 25 degrees, the pressure is about 1.2. I mean, like there are so many facts about the world that doing the rule-based, let's just explore all the possibilities, I get stuck. There's too many. It's like Go. So we couldn't solve Go, the game of Go, even though we could solve chess. So the game of Go is very much like chess. It's a 2-player, perfect information, zero-sum, alternating player game. Mm-hmm. I take a turn, you take a turn, I take a turn, you take a turn. But Go is played on a 19 by 19 grid, or is it a 28 by? I don't know. It's big. Yeah. It's a big grid. And so the branching factor, the number of possibilities at each stage, is way bigger than chess. And so it turns out we had no hope with Go. Also, we couldn't write down the heuristics. So we just couldn't do that, and we couldn't do real-world situations because there was just too much that could be relevant. And so the computer had to search everything, and it turns out, that takes the age of the universe to search, and we can't do it. Okay. So in machine learning, we pulled a clever trick, which is we said, let's do the following. So what is it? So I'm trying to recognize a number, like a handwritten digit, like a handwritten 7. Okay. So first of all, I need to capture the question in a way the computer can get a hold of it. So what I do is I take your handwritten digit and I take a picture of it and I digitize it into a grid of pixels, which are either white or grey. Okay, so at least that gets it, and maybe I scale it to fill the grid and make sure it's that's what I'm asking you to do. So is this grid of pixels, and I'm asking you to recognize what digit is that? Okay. Supposing I had some way to tell you whether one grid of pixels, and I'm deliberately not using the word image because I just want to make it as almost abstract as possible. Whereas one set of numbers, representing a 28 by 28 grid of pixels, is similar to another.
Yeah.
Supposing I had some way to compute a similarity between the two.
And then in this example, those set of pixels are referring to the images of the handwritten digits.
Yeah.
Which we're trying to
Recognise.
recognise.
Exactly.
But maybe more like the shade of the pixel, for example. So if it's dark or white.
Yeah. So here's what you could do. You could. I don't think they do this, but you could sort of overlap the images, subtract the numbers at every pixel, take the absolute value and add all those up.
And that would be like a good heuristic of number 7.
Yeah, it's a guess at a way of saying whether two images are similar. It's not a very good one because actually, if I rotate one of my 7s a little bit, that's still a 7. Whereas if you overlay them and subtract the pixels, but with a little bit of thought, you can come up with a reasonable way of saying whether one image is like another image or very different.
Yeah.
So if you overlay a 7 and a 0 and just look at where the pixels don't match, they're pretty different, right?
Yeah.
So that's step 1.
Come up with a similarity
measure. Now, I will admit that I'm massively oversimplifying what's actually going to happen in the end, but just bear with me for a second, because I think this is a good enough way of thinking about how it works that it'll let you correctly answer most questions about will it work without understanding the full detail. Okay. Now, suppose, as well as that, I'm going to give you a lot of solved examples. So I'm going to give you, in this case, 60,000 little images with the pixels, all of handwritten, lots and lots of different handwritten digits captured from all people, every single one of which I'm also going to tell you which digit it is. I'm going to get a person to say, well, that's a 3. 3. Okay. So now, here's what you could do. I give you a new pixel representation. You take it and you just say, is it like that one? 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 And you find all of the examples that I've given you already, which are kind of like this one in the simple way that I've described. Not are they like a 7, but just as pure black and white pixelated images.
Sure.
Are they similar? Then you look at all those examples that you found that are similar, and you're like, oh look, they're all 7s, or 90% of them are 7s, 5% are 1s, and I don't know what the other 5% are. So what are you going to get? Probably a 7.
Yeah. That's machine learning.
Pretty much. Okay. So in practice, that's not what we do, but in principle, I think that's a good enough model that lets you answer questions about what do you need to say that machine learning can work, right? You're going to need, one, a way of saying somehow if two things are similar. And it turned out with images, right? It turns out that convolutional neural networks, which work a bit like the retina, actually, it turns out they're actually quite good at image similarities, rotations, and when it's actually over there, but when it's
So they don't simulate those differences. They work on this kind of encapsulated understanding of the relationship from this training data set, those images that have the label of the number with. Or do they do that kind of simulation based, if we turn it around slightly like this, if we zoom in a bit more, if we zoom out a bit more,
Yeah, they don't do that.
Yeah.
They don't do that. So I'll come back to what they do in a second. But anyway, so in principle, you need a way of saying, and it doesn't have to be great, because the other thing you need is a lot of solved examples. And with enough solved examples, you can get away with an unintelligent version of similarity, right? So for images, it turned out that we invented a way of thinking what similar was, which is not the same as we use for speech and not quite the same as we use for other things, but it worked quite well. And in addition, given this large example set, you're doing quite well. So you need quite a lot to make machine learning work.
Okay.
So some claims are clearly false because you clearly don't have those things.
So to bring this full circle then, I think what you're getting at here is that the amount of work needed to make machine learning seem intelligent is almost comparable to the amount of work needed to make other forms of AI seem intelligent. And therefore, it's a different toolbox, a different suite of... And there are a different set of problems to which it is applicable, but to say that one is AI and one isn't wouldn't be totally fair. So
I think that's right.
We should either say none of them are or all of them are.
Yeah, I think it's clear that all of them are. None of them are artificially general intelligent.
Yes.
They're all AI. And yeah, I think they're limited in their ways. So, I don't know, you could ask me, what have I been not telling you about machine learning? Because there's quite a bit I've not told you.
Of course, yeah.
You could also ask, and then there's also, of course, people aren't crazy. The next thing is, well, okay, can we squish these kinds together? Can we do a bit of everything? And it turns out people do that, and that works really well in certain cases.
Yeah.
And you can also say, like, what's missing? But anyway, it turns out I have time now because my wife is in fact going to pick up my son.
Well, James, on that note, thanks very much for joining us on the podcast and talking about the problem of AI. I think we got to a really pretty good resolution there in everything's AI or nothing's AI in computing. That's
and it's
what...
not all incredibly intelligent, but intelligent enough.
I mean, it's really clever, right? I don't want to downplay stuff. Like,
one thing I would say is if there is ever an quote-unquote AGI, artificial general intelligence, then we certainly won't call any of this stuff AI. But that would certainly change our conceptualization. But until such a time, I think I'm gonna fall down on your side of the fence and say it's all AI. All right, James, thanks again for coming on the podcast.
Great pleasure, thanks for having me.
Before we let you go, where can people find out more about your research online and things that you're working on? So there's a little bit about NoCell on the Turing Institute's website. Just search for NoCell. Not a lot. And the thing about what I'm doing... I know that you're not a social media person, so I will not ask you for your Twitter account.
I have nothing. And the biggest thing that I'm worried about right now is what does the research engineering group look like over the next few years to support what the Turing will look like over the next few years, which is also not online. But that's what I'm worried about.
All right, brilliant. Okay, thanks again for coming on the podcast, James.
Not at all, thanks very much.
If you have an interesting topic you'd like featured on the show, a guest recommendation or a burning question, email podcast@turing.ac.uk.
The Turing Podcast is hosted by Ed Chalstrey, B. Costa Gomez and Joe Dungate and produced by Dan Whitfield for the Alan Turing Institute.
Music for the podcast was provided by Jam and Sun. You can check out his latest releases at jamandsun.bandcamp.com.